So exponential decay functions, all right. Remember, so from yesterday, we looked at y equals 2 to the x, okay? And this was a growth function. Why? What made it growth? The 2, right? 2 is greater than 1, so growth. Okay? Today, we're going to look at b values, right? This is b, right? The base of our exponent. B values between 0 and 1. Between 0 and 1. So today, let's look at, well, a b value between 0 and 1. Let's try like 1/2 to the x. Okay? And let's see what we get here. All right. So again, I'll make a little table. So I'll do a vertical table here. Let's just use the same values we did yesterday. So I'll say -3, -2, -1, 0, 1, 2, 3. Okay. And again, this is for y equals 1/2 to the x. Okay. So let's start with the easier ones, right? What's 1/2 to the first power? 1/2, right? Okay. What's 1/2 squared, or 1/2 times 1/2? 1/4, right? And what's 1/2 times 1/2 times 1/2? 1/8, yeah, okay. What about 1/2 to the 0? Anything to the 0 power is going to be 1, except for 0. 0 to the 0 power is actually indeterminate form, but anyway. Okay, and then what about 1/2 to the -1? Yes. 2 is exactly right. How about -2? 1/2 to the -2? 4. 1/2 to the -3? Careful. Look at what we're doing every time. Times 2, yeah, it's 8. Times 2, times 2, times 2, times 2, 8. Yeah. We're going to go backwards. You want to multiply by 2 as you go backwards. Okay? So let's plot these points. Okay, and I'll put this in red so it stands out. Okay, so -3, 8. -2, 1, 2, 3, 4. -1, 2. 0, 1. And again, CJ, just to kind of, re-emphasize that there. There's that 0, 1 y-intercept showing up here. So again, regardless of whatever our parent function is, whatever the base is, you're going to have that 0, 1. For the parent function, without any other transformations, you'll have 0, 1. So there's that point again, that important point we want to keep. Okay, 2, 1/4, and then 3, 1/8. Okay? So I'll connect those dots there. Something like that. Okay. Do the same thing we did yesterday. Talk about domain and range. Okay. What is the domain of this graph going to be? -infinity to infinity. Yep, you got it, right? We can put in any x value we want here. There's no way we could divide by 0. There's no way we could take the square root of a negative here or anything like that. So yeah, the domain is -infinity to infinity. Okay, and just like yesterday also, is the range -infinity to infinity? No. What's our lowest y value here? What's that? Yeah, we're going to go closer and closer and closer to 0, but we'll never get there. And then what's the highest y value we have? Infinity. Okay. Please do not put infinity to 0 here. Please do not put infinity to 0. I know if you look from left to right, yes, you're going from positive infinity down to 0 here. Remember, range, you're always describing the range from the bottom to the top, from the lowest y value to the highest y value. Just like for the domain, you're always describing it from left to right, right? For the range, you're always describing from bottom to top. Okay, so please make sure you still describe, that the correct way. Okay? All right, let's see here. Does this graph also have a horizontal asymptote? Yeah. Where's the horizontal asymptote? Y equals 0 again. Yep. Still has the y equals 0 horizontal asymptote, right? That's a product of this range here. As we approach, the y value of 0, we're getting closer and closer. We never get to it, right? So that's indicating a horizontal asymptote. Alrighty. Let's see here. What else did I talk about yesterday? Let's talk. Is this function ever increasing, decreasing, constant, some combination of those three? What? It is decreasing everywhere. So decreasing negative infinity to infinity. Okay? And then what about the y-intercept here? Yeah, it's going to be 1, right? Y-intercept is at 0, 1. Okay? Do we have any x-intercepts here? No, right? The graph's not going to cross the x-axis because we have that horizontal asymptote there, right? Now, of course, if you shift the graph up or down some, well, not up. If you shift the graph down some, it will cross the x-axis. But with the parent function here, 1/2 of the x, it will not. Okay? Questions on anything there? So why do you guys think we call this a exponential decay function? What about this graph is indicating decay? What's happening with the graph? Why would we call this decay? It's decreasing. Yeah, that's all there is to it. Yeah, it's decreasing. Yeah, since we're decreasing everywhere, this is exponential decay. Okay, versus yesterday, right, when we graphed stuff, right, this is called exponential growth because as you go from left to right, we are increasing everywhere, right? So decreasing everywhere, increasing everywhere. By the way, you notice a similarity here. I don't know if you guys can see it. You probably can't see it. Let me just do it this way on the graphing calculator. Okay. Show you here. So yesterday we graphed 2 to the x. Today we're graphing 1/2 to the x. Okay? And what kind of relationship do you see between 2 to the x and 1/2 to the x? So there's 2 to the x. There's 1/2 to the x. What kind of relationship do you see there between those two graphs? They are reflections over what? The y-axis. Yes. Okay. Yes. So if I were, for example, if I did like 3 to the x and maybe did 1/3 to the x, you can see we expect the same thing. There's 3 to the x, there's 1/3 to the x. And you see you get the same thing. Okay? So yes, those are reflections over the y-axis from one another. Okay? Good. Any questions so far? All right, let's do one transformation then, and then I'll talk about the growth and the decay factor and the decay rate as well. Okay, the decay factor and the decay rate as well. All right, so let's do this here. So let's graph g of x equal to 3 times 1/2 to the x minus 2 power minus 2. Okay, what kind of transformations do we see here? Okay, stretch by 3. Sorry, let me. What else? Shift down 2. What else? Right 2 as well. Okay, so again, you can kind of picture in our head, here's that 1/2 x graph right here with our horizontal asymptote at 0. Right, imagine shifting this graph right 2, down 2. So right 2, down 2, okay? It's going to look something like this maybe. Okay? Stretch by 3, so it might be it's going to be a little bit steeper than this graph is too. Okay, it's going to be a little bit steeper. So let's go ahead and graph this thing, all right? Again, we're going to use just a table of values to kind of help us out here. Okay, let's use our table of values. All right, so I'll go ahead and make an XY chart here. Okay, again, normally our y-intercept is at 0, 1, right? But we're going to shift it to the right 2, right? So instead of having 0 in the middle, I'm going to shift everything right 2. That means I'm going to start at 2 in the middle. That means we'll go back to 1, 0, and forward to 3 and 4, like that. Okay, if you want to get more points than that, you can. I know I got like 7 here, but we can just do, I think 5 should be fine. Okay. Again, you can also take turns plugging it in, okay, or you can, just use your graphing calculator to fill out those values too. I'm going to plug them in real quick because I don't think it's that bad. So let's see here. This will be 3 minus 2, 1, and then 1 minus 2 is negative 1, 2, 6, 4. Okay, and then negative 2, 4, 3, 12, 10. Okay, and then 3 minus 2, 1 half, 3 halves. 3 halves minus 2 is 1 half. And then 4 minus 2, 2, 1 fourth, 3 fourths, 3 fourths minus 2. Oh boy, negative 5 fourths. Okay, let me check my math here just to make sure I did that right. Okay, so again, I'll type in my calculator here. I'll type in the 3 parentheses 1 half to the x minus 2. Okay, again, if you have the pretty type, the math print like I have, you don't need to worry about putting parentheses around your exponent. But if you don't have this like pretty math print type, you need to put parentheses around your exponent, and you should really put parentheses around your base too. Okay, so parentheses around the base and exponent. Okay, please don't make that mistake. All right, I gotta go. Whoa, I'm way too far negative. Oh, I forget the minus 2. You right. Okay. All right. So let's see here. 0, 10, 1, 4, 2, 1, 3, negative 0.5. Whoopsies. And then 4, negative 1.25, which is negative 5 fourths. Yep. Okay. Let's plot these points then. Okay. Ooh, 0, 10. That's not going to quite fit. Let me see if I can make it fit. No, I don't want to do that too much. 1, 2, 3, 4, 5, 6. Okay. So now, let's go ahead. I'm going to put in my horizontal asymptote here as well. Okay. Again, normally the horizontal asymptote is at what y value?
1.
At 0. Horizontal asymptote. The y-intercept is at 1. The horizontal asymptote is 0. Okay. We have a horizontal asymptote at 0 normally, right? See, like right here, horizontal asymptote at 0. Whoop, you can't see. There you go. Horizontal asymptote at 0. Okay. For our purposes, though, we're shifted down 2. So where's our horizontal asymptote going to be now? Where's the horizontal asymptote going to be now? If we start at 0 and we shift down 2, where will the horizontal asymptote be? Negative 2. Okay, there's our horizontal asymptote there. And let's plot these points. 0, 10, I can't fit it. Let me see if I can just like kind of imagine it. 6, 7, 8, 9, 10, something like here. Okay, and then 1, 4, 2, 1, 3, negative 1 half, and then 4, negative 5 fourths. Okay, and there's the graph. Question?
So this goes down first, but the horizontal asymptote is 0, and it's affected by the decay value?
Yes. That's not stupid. That's good summarization. Yeah. Okay. Because again, you think about it, right? A horizontal line, you shift that left or right, it's still going to be the same horizontal line, right? Because it's the same location. But shifting it up and down, that's going to change its location. So that's why we don't worry about the minus. I mean, you can shift your horizontal asymptote right to if you want to. It's still going to be the same horizontal asymptote. But the down to, that's what affects it. Okay? Yeah, no, that's a great question. Other questions? All right. Then I just want to talk again real briefly then about these exponential decay like factor and stuff like that too. Okay, so and the exponential decay function. Okay, so let's take a look here. Ooh, goody! I was hoping they would have an example like this. Okay, that I could use. Okay, so let's just see here. Let me make sure. I kind of want to be a little bit consistent with how I did things yesterday. Okay, so again, in word problems, we're not going to worry so much about H and K, okay? In word problems, we're not going to worry so much about shifting left or right, up or down at all. We're going to mostly worry about, you know, well, you'll see here. This, yeah. Okay. So in word problems, I'm going to give you one or two here today for your homework as well. Okay. We don't really worry about H or K, shifting this left or right, up or down at all. Okay. It's more just like we have A, like a stretch, and then B, that's going to be like our growth factor or our decay factor. Okay. So remember, I told you guys in the warm-up there, it's still on the board, but I'll put it right here too. The A in these word problems is our initial or starting amount. Okay. The B, that is our growth or decay factor. Okay, now growth and decay are opposite ideas, right? So how can B be opposite things, right? How can it be both a growth or a decay factor? Well, it's the value of B. It's what number you put in for B that determines whether it's a growth or decay. If B is bigger than 1, we know it's going to be a what kind of factor? Growth, right? If B is less than 1 but greater than 0, we know that's going to be a decay factor, right? So, yesterday we saw on the notes, right, that we were talking about a guitar increasing in value by 9% each year, right? And so the 9%, that was our growth rate, that was our R value, okay? And so therefore B would be 1 plus that R value. So 1.09 would be our B, the growth factor there, okay? But let's change it up here, and instead of a guitar appreciating in value, let's talk about the value of a truck. Okay, and let's just say purchased new. Okay, for $28,000, which, does $28,000 buy you a truck nowadays? I don't even know. Okay, decreases by 9.5% each year. Okay. So let's write an exponential function for this. Okay. So what's our A value here? What's the starting or initial amount, or the starting or initial value for this truck here? What's A? $28,000, right? Yeah, what you bought it for is what it was worth, right? Or at least because you bought it for that amount of money, it was worth that amount of money to you at least, right? So we're going to decrease by 9.5% each year. Okay, how do we factor that in? So since it's a decrease, bless you, that means our B is going to be a growth factor or a decay factor. Decay, because we're decreasing, right? We're decreasing in value. So that means B won't be equal to 1 plus R. B is going to equal 1 minus R. Okay? B is going to equal 1 minus R. Okay? What is our R in this scenario? What's our decay rate? 9.5%. So R is equal to 9.5%, which is equal to what decimal? So careful, 0.95 would be what percent? That'd be 95%. What is 9.5%? 0.095. Yeah, 0.95. Okay, let me zoom in over here. Maybe this will be more helpful right now. Okay. So then our R will be, or sorry, B is equal to then 1 minus the R value of 0.095. Okay? Which means then that B, if I do that, 1 minus 0.095, let's see, minus 0.09 would be 0.91. So 0. No, messed up. 0. Nope, that was right. 0.905. There we go. Okay, that's our B value there. Okay. So, the formula then would be y equals A, 28,000, times B, 0.905, to the t or to the x, however you want to, whatever variable you want to use there. Again, t is used because we're typically talking about a time, the decay over time kind of thing. Okay. So there's our equation that would describe how the value of the truck decays over time. Now, let's, just for the fun of it, okay, let's predict, or let's not predict, let's determine how long it will take the truck to be worth $5,000. Okay, so your $28,000 truck. Let's predict how long it'll take for the truck to be worth $5,000. Okay, so we'll plot this in our graphing calculators here. We'll type this into our graphing calculators. Let's see if I can get this all to fit on my screen at once here. Okay, so 28,000 times 0.905 to the x. Okay, and we'll go to our table. Okay, so after 1 year, let's see if I can zoom in on this maybe. After 1 year, the truck is now only worth $25,000. Okay, after 2 years, the truck will be worth 22, almost 23,000. 3, 20,700. You see, so on and so forth. Okay, and as we go lower and lower, all right, so there it is, right? During what year will the truck be worth $5,000? Year 17, right? Between year 17 and year 18, it goes from $5,130 to $4,643.40. That seems like a pretty decent estimation of things, I'd say, right? I mean, getting 17 years use out of a truck seems about right. Maybe, I don't know. Okay. So anyway, so there's the idea, right? Okay, you go from your $28,000 buying it brand new, and then 17, almost 18 years later, right? $5,000 is what it's worth. Okay? So that's the decay. Biggest thing you want to be careful with here, right, is that decay factor, or the decay rate, I should say that, right? Change that decimal, change the percent to a decimal, right? And then do 1 minus here because it's a decay. If it was a growth, you'd have 1 plus then, right? Of course, 1 plus. All right, questions on any of that? All right. So then the rest of the time, I'm going to give to you guys to work on the homework here. Okay, so this is going to be in section 13.2. I'll get you the page numbers here in just a second. Numbers 1 through 4. Okay. Again, you're just describing transformations. Okay. I'd also like to do numbers 5 and 6. These are graphs. And domain range. So very similar to yesterday. And then number 9 is going to be where you write the graph. All right, and let's do 11 as well. Okay. number here for that section is page 481. Page 481.
So what section?
It's on the board there. 13.2.